What's my blood pressure? 120/80. Wow, I'm healthy. Oh, wait a second. This isn't a medical device. Let's talk about pressure. And in particular, we're going to talk about pressure in the context of mostly hydrostatics today. So, let's get started. So, we're basically going to be talking about hydrostatics and pressure. Pressure today. No, not that kind of pressure. Pressure in the context of fluid mechanics. So, what's the plan? We're going to talk about pressure versus shear stress, and how they're both essentially forces per unit area, but there's some key differences between them. We're going to talk about the pressure gradient, what it is. Essentially, spoiler alert, it's a spatial derivative of the pressure. So it's a derivative of pressure with respect to space. And it's actually the pressure gradient that causes forces on things. So pressure in an absolute sense, not particularly important. It's pressure gradient that really gets stuff moving in fluid mechanics. We're going to talk about, and once we talk about pressure gradient, this will inform us talking about net forces on chunks of fluid. Right. So in mechanics, we followed Newton's laws. It said sum of forces equals mass times acceleration and stuff like that. We'll be, in statics, you said sum of forces equals 0. So in hydrostatics, we're going to be talking about net forces on chunks of fluid, and the formulation is going to be a little bit different, but a lot of the concepts carry over from mechanics. And once we talk about net forces on the chunks of fluids and what sort of special cases exist in hydrostatics, we'll be able to work out relationships between pressure, depth, density, and gravity. And all this will come together in one single equation that's going to be useful in solving problems that involve hydrostatics. So let's start off by talking about pressure versus shear stress. So when we talked about shear stress in previous lectures, we oftentimes imagined a chunk of fluid, and when we talked about shear stress, we basically said, hey, yeah, shear stress is a force it's a force applied to a unit, applied to a surface, and it has units of force per area. But the key thing about shear stress is a force that's applied parallel to the surface. So shear stress is parallel to surfaces. So for example, if we had some chunk of fluid right here, and there were shear stress applied to this fluid, then by our convention, on the top surface we would have shear stress applied tangential to the surface like this, and on the bottom we would have shear stress applied like this, right? And it's possible to have shear stress applied in the other direction. It would just be negative in that case, right? So so this is the essence of shear stress. Pressure is similar in many ways to shear stress, but has some key differences as well. So it's still useful to sort of think about these things, as in terms of chunks of fluid. Pressure is still force applied to a surface, right? So it's the same. Right? It's still force applied to surface. It still has units of force per area, but the key difference between pressure and shear stress is pressure is associated with forces normal to the surface, right? So it's associated with force so there we have it. And shear stress kind of had this funky convention where on the tops of the surfaces it was pointing to the left, and on the bottom of the surfaces was pointing to the right. So this was our convention for shear stress. Our convention for pressure is that positive, so this is our convention for positive. This is our convention for positive shear stress. Our convention for positive pressure is that it acts inward on a chunk. So if I'm thinking about, hey, what is pressure doing to this chunk of fluid? Pressure is acting inward. So if pressure is positive, then pressure is acting inward on this chunk of fluid. And it is possible to have pressures that can pull on things. It would just be negative in that sense, right? So if I say, okay, I'm defining by convention pressure's acting inward, and if in physical reality pressure's pulling outward on something, then the pressure will just have a negative value, right? So this is the convention. So pressure is still a force applied to a surface. It still has units of force per unit area, right? So in SI, that would be newtons per meter squared, or if you want to give it the special name that is equivalent to a newton per meter squared, Pascal. It's just pressure is normal to a surface, shear stress is parallel to a surface. And in real life, we could hypothetically have chunks of fluid that have some force that's kind of at some oblique angle to a surface, in which case you could decompose this force as some equivalent amount of pressure and shear stress, right? So having pressure and shear stress kind of covers all of our bases. All right, so that's the key difference between pressure and shear stress. Now let's talk about pressure gradient. So we'll talk a little bit about pressure, and pressure gradient, and this will sort of start us in this kind of mathematics, calculus, algebraic way of analyzing pressure. So when I think about the pressure gradient, before we talk about the pressure gradient, we sort of need to talk about how pressure can vary. So how can pressure vary in fluid mechanics? Well, in general, pressure can vary with time, right? I could have a balloon, I could pressurize it to some pressure, and then if I come back an hour later, that balloon could have a different pressure inside of it, right? So we know pressure can vary with time. Pressure can also vary spatially, right? So when I think about spatial variation, it could vary with x, y, or z, right? So we know that if I were sitting at the top of a pool of water, I might be at some pressure, but if I were to swim all the way down to the bottom of the deep end, I would be experiencing a much larger pressure. So we know that pressure can vary spatially, and for some tricky flows, pressure can vary both with time and space. So that can be potentially complicated. Pressure can vary with time and spatially, and oftentimes it's the spatial variation that can drive flow. And of course, we'll get to this later on in the class, but if you have some tube and you have a high pressure at your inlet and a low pressure at your outlet, then it's the difference in pressure between the two ends that can end up driving fluid through the pipe, something like that. But of course, this is hydrodynamics, we're going to be talking about hydrostatics today, but in hydrostatics, even though we're not talking about pressure driving flow yet, there are still spatial variations in pressure that are important in the context of fluid mechanics. So let's talk about the pressure gradient. So net pressure forces exist when there is spatial variation in pressure. So what do I mean by that? Well, let's imagine I have a block, and you could just imagine that this is a chunk of fluid, right? Something like that. So let's say I have this little chunk of fluid right here, and I'll try to draw a 3D version of it. Right, and let's give myself a coordinate system. Let's do. All right, so imagine I have this coordinate system right here, and I wanted to say, hey, there's pressure acting. Let's say there's pressure acting on this chunk of fluid, right? So if we think about pressure, if you recall back from the previous page of notes, positive pressure is defined by definition to be inwards. So if I have pressure acting inwards on this block, I might, let's say, have some pressure acting on this face. I might have pressure acting on this face as well. And if these pressures are equal, if the pressure here on this face is the same as the pressure on this face, then the forces from those two pressures would end up perfectly canceling out. So if the pressures are equal, then they cancel out. Then forces out. And this is true no matter what the magnitudes of these pressures are, right? I could be in a near vacuum in space, and the forces could be two small forces but potentially equally canceling out, and I could be at the bottom of the Pacific Ocean, and these two pressures could be huge, but unless there's spatial variation in the pressures, I don't end up getting any sort of net force. And a lot of times only interesting things really happen in fluid mechanics when we get net pressure forces. So if the pressures are equal, then the forces cancel out. Or conversely, if these pressures are unequal, then we're going to get a net pressure force, which is oftentimes where the interesting stuff arises in fluid mechanics. So if we have a difference in these pressures, that means there must be some spatial variation in pressure here. So actually, I'm just going to change up my coordinate system just a little bit. I'm just going to call this X, Y, and Z. Sorry to switch up my letters a little bit, but I just wanted this to be X to be consistent with the other notes that I have. So we have X, Y, and Z right here. So there we have it. So imagine I have this block, right? And I'm just going to call this at point X, and this face, let's say, is at location X plus delta X, right? If we're separated, if the face of this block has a distance X plus delta X. So what does that mean? If I have a difference in pressure, the pressure is going to be different at X than it is at X plus delta X. So how does that play into a pressure gradient? Let's consider that. So let's try to work out net forces due to pressure. So I might call the pressure on this face let's call this pressure at position X. And similarly, the pressure at this case would be pressure at X plus delta X, right? So pressure is a function of, potentially all of these things. Right now, we're sort of just considering it to be a function of X, right? So if we have pressure at X and pressure at X plus delta X, we might get net forces due to that. So let's say I have this cube. Let's say it's delta X in this dimension. And then let's say it has a dimension delta Y in this dimension. And let's say the chunk has a delta Z in this dimension, right? So this is a block. Its dimensions are delta X, delta Y, and delta Z. So let's see if we can work out what the net force is on this chunk. So let's look at what the net X. Let's look at what the net X pressure force is, right? So when I think about net forces, well, if we look back earlier in the notes, pressure is force divided by area. So if I want to get the force from a pressure, I need to multiply that pressure by the area of the face it's acting on, right? So to get forces, I need to multiply the pressure times the area that pressure is acting on. So in this case, there's pressure acting in the X direction on two relevant faces. Strictly speaking, there is pressure acting on all of those other faces, but they're either pushing it in the Y direction or in the Z direction. So we only really need to consider pressure on those two faces. So if we're looking at the net X pressure force, in this case, it would be the force associated with this left face and the force associated with this right face, right? So the net force due to pressure in the X direction is going to be equal to this pressure times this area. So let's call it pressure at X times the area that this pressure is acting on, which would be delta Y times delta Z. So that's associated with this first force here. And if we think about it, positive pressure is defined to be acting inwards, and on this left face, it's the force would be acting in the positive X direction. But if we think about pressure acting on this other face here, we'd need a minus sign associated with all of this because this pressure is acting in the negative X direction. So let's work that out. In this case, the pressure on this face would be pressure at X plus delta X. And the force associated with this pressure would be the pressure times the area of the face that this is acting on, which would be delta Y times delta Z. So what does that what does that mean? Well, we can sort of factor out some like terms here. And what do we get? So we could basically say we'd have a minus sign. I'm just going to factor out a minus delta Y delta Z. So we have minus pressure at X plus delta X minus pressure at X. And I'm just going to be a little cheeky here, and I'm going to factor out a delta X, delta Y, delta Z. So if I factor out a delta X that wasn't actually in here, I could put it in the denominator here and the numerator out here, and I'm not cheating. The mathematics police aren't going to come arrest me. So what does this look like? Oh, sorry, I'm out of the frame. So what do we have? The net force due to pressure is these terms, and I could I could sort of both multiply and divide by delta x, and I could factor out a delta y, delta z. All right, so let's now divide both sides of this equation by delta x, delta y, delta z. And what do we get? Well, here we get sort of a force per unit volume on the left-hand side, and then on the right-hand side, we get this term here. So, but let's take a closer look at this term right here. If I looked at this term and sort of took a limit, what would I get? Well, if you look at here, this is essentially the definition of a derivative right here. So if I took a limit of this quantity right here, after I divided both sides by delta x, delta y, delta z, I sort of get my net pressure force per unit volume is going to be equal to, and this term here, if I took limits as delta x approaches 0, this essentially becomes a derivative in calculus. And strictly speaking, it would be a partial derivative with respect to x, and it's a partial derivative because hypothetically pressure could be a function of many variables. So when something can be a function of many variables, and you're just considering its derivative with respect to one of them, you got to think about partial derivatives. So in this case, it's partial p partial x. And again, we'll deal a little bit more closely with partial derivatives versus ordinary derivatives later on in this class. So if this feels a little daunting right now, don't worry too bad. We'll sort out partial derivatives versus ordinary ones later. So this is the net pressure x force per unit volume is this right here. And this, well, just this part of it, this partial derivative of pressure with respect to x, is what we call the pressure gradient. So how did we get at this pressure gradient? We basically said, hey, let's say we had some chunk of fluid and we had different pressures acting on the two faces. If we have different pressures acting on the two faces, then basically by definition, pressure must be varying with x. If pressure is varying with x, then pressure's derivative with respect to x is not 0, right? So if we have a non-zero pressure gradient, then we have a non-zero net x force on some chunk of fluid due to pressure, right? If I have a difference in pressure on this face versus this face, then pressure's changing with x, so it has a non-zero derivative with respect to x, and that means that there must be net forces on it due to pressure. All right, so we've talked about, what is the pressure gradient? It's a spatial derivative. We talked about what is the pressure gradient. It's a spatial derivative of pressure. It's a derivative of pressure with respect to some spatial variable, and it basically is roughly equivalent to, or it results in net forces on chunks of fluid. But so if we want to talk about net pressure forces, they're going to come from pressure gradients, but that's not the only force that can act on chunks of fluid. So let's now talk about other forces that could sort of act on a chunk of fluid. All right, so let's think about net forces on a chunk of fluid. So imagine I had some chunk of fluid and we wanted to analyze all of the forces that could be acting on this chunk of fluid, right? So let's do x, y, and z right here. So let's sort of think about it. Maybe perhaps pause and ponder what types of forces could be acting on a chunk of fluid. Well, let's work some of them out, right? So if I think about chunks of fluid, we already said pressure could be acting on some chunk of fluid. We talked about shear stress. That could be acting on a chunk of fluid. And also gravity can act on chunks of fluid as well. Yep, so pressure, shear stress, and gravity can act on chunks of fluid. And if I wanted to think about this fluid, right, if I wanted to think about chunks of fluid, I might consider, hey, if I have some chunk of fluid, Newtonian mechanics applies to it, right? If I want to consider, hey, all of these forces could be acting on this chunk of fluid, and if I want to consider net forces of this chunk of fluid, then that's going to result, then sum of forces is equal to mass times acceleration, right? So let's square it out. So if I wanted to analyze this chunk of fluid, I might say the net pressure force plus the net shear stress force plus the gravitational force has to be equal to the mass of this chunk of fluid times its acceleration. And strictly speaking, all of those should be vector quantities as well. So we could square this out, but I ask you to pause and ponder right now, right off the bat. If we're just going to go straight to hydrostatics, right? If we're going to go straight to hydrostatics on this chunk of fluid, if we go straight to hydrostatics, what simplifications to this sort of above equation? What simplifications can we make? Well, if you pause and ponder, if we're talking about hydrostatics, can there be any acceleration? Well, if something's static, it wouldn't even have any velocity. So if we're talking about hydrostatics, no acceleration, right? If we're talking about hydrostatics, we don't even have any velocity, and there's no acceleration. Can we make any other simplifications? Well, actually, yeah, we can. If this is a fluid, can there be any shear stress if we're talking about hydrostatics? So think about it. Pause and ponder part 2. Can there be any shear stress in hydrostatics? Well, the answer is actually no. So we can get rid of this shear stress too, right? Where does shear stress come from? In fluids, shear stress comes from a velocity gradient. So if shear stress comes from a velocity gradient, if we're talking about hydrostatics, where the fluid's not moving, there's no velocity. And if there's no velocity of these fluids, then there's no velocity gradient either, right? So what does this mean? In hydrostatics, we're just talking about a balance between pressure and between gravity. So hydrostatics is essentially just the balance of pressure and gravitational forces such that they sum to 0. That is the essence of hydrostatics. All right, so let's square away what the net pressure force and the net gravitational force would be on some chunk of fluid in hydrostatics. So usually in hydrostatics, we choose to define our coordinate system with z pointing up, and let's say x and y, something like this. X and y usually don't matter too much in hydrostatics. We're mostly concerned with z. And we choose z pointing up, and we choose to have gravity pointing downwards. So usually we define our coordinate system in a way like this, such that gravity is in the z direction and pointing in the minus z direction. Usually this is pretty convenient, right? And we have some chunk of fluid that we're choosing to kind of analyze in a coordinate system like this. And ultimately, what are we trying to do in our analysis of hydrostatics? Well, we're sort of looking to fully flesh out. We're looking to fully flesh out net forces on chunks of fluid, and in this case, it's going to be pressure and gravity. Right? So we know that it's going to be pressure and gravity for hydrostatics. And we're looking to develop a relationship between pressure, depth, densities of these fluids, and gravity. So this is what we're trying to work out. All right, so in developing this relationship, it's helpful to define sort of z in your, z pointing up, gravity pointing down, and x and y to be perpendicular to that. So if we're analyzing this chunk of fluid, let's kind of give it dimensions like we had before, right? So there's going to be this dimension of this chunk of fluid is delta x. This dimension of this chunk of fluid is going to be delta y. This dimension of this chunk of fluid is going to be delta z. If I think about this chunk of fluid, I might call the location of this bottom face, I might call it at location z, and the location of this top face, the top face would be at z plus delta z. And then if I think about pressures acting on this chunk of fluid, well, pressure is defined in such a way that it acts inward on these, and I would call the pressure on the bottom face pressure at z, and the pressure on the top face pressure at z plus delta z. Right, so we'd have these, and these pressures don't necessarily have to be the same, and in fact we expect them not to be, right? If we go to the bottom of the pool, we change our z, then we get to a different pressure. So this is going to help us. We also know that this chunk of fluid is going to have gravitational forces on it, right? So we're essentially also going to need to work out what the mass and essentially the weight of this chunk of fluid is as well, right? So we're gonna analyze pressures to help work out what the net z force due to pressure is. We're also going to analyze mass to help deal with mg as well, right? So we have this chunk, we have pressures. We're going to need to work out the mass because basically the gravitational force on this chunk of fluid the gravitational force is going to be mass times g, and it's going to be pointing in the minus z direction. So, yikes, we have a lot of work to do. Okay, so let's first analyze pressure, and then we'll try to square away what this gravitational force is, and then hopefully we can get some kind of relationship between pressure, gravity, density, and depth in the fluid as well. So let's do that. All right, so here we are. All right, so first let's analyze pressures, right? So if I'm thinking about it, I want to think about forces in z. I'm going to have a positive force due to pressure at location z, and in order to go from a pressure to a force, I need to multiply this pressure times the area of the face that it's acting on. So pressure times delta x times delta y is going to be the net force due to the pressure on the bottom face, and that's positive because it's be pointing in the positive z direction. So so there we have it. there's pressure acting on the top face pointing downwards. So it would be pressure at z. So I have a minus pressure at z plus delta z. And that's going to be times the area of this top face, which would also be delta x times delta y. So there we have it. And now, finally, we need to analyze this gravitational force. So if we're in hydrostatics, 0 is going to be equal to the sum of all the forces. So we're going to have to deal with this gravitational force as well. So what's that going to look like? So we still have some work to do here. So we know in general gravitational forces is mg, but a lot of times, here we've sort of defined a kind of goofy, kind of arbitrary chunk of fluid. Oftentimes, if we're thinking about fluids, it's useful to talk about fluids in terms of their densities, not the mass of some chunk of fluid. Right. So it would be nice, if I could work out a relationship in terms of density rather than in terms of just mass, right? Because my drawing of this chunk of fluid was somewhat arbitrary, whereas density, density is sort of a real, more physical quantity, right? So can I work out this gravitational force not in terms of mass, but rather density? Well, if you dust off your high school chemistry notes, you would know that in order to go from mass to sort of express mass in terms of density, you could multiply the density of the fluid that's in this chunk times the volume of the chunk in order to get its mass. So mass of fluids, I would multiply, I could express in terms of density. And I want to make a distinction here between what I'm drawing as the Greek letter rho, which I'm giving a little curly tail, in contrast to p. So density is Greek letter rho. So Greek letter rho is going to be density. Capital P is going to be pressure. And these two are different from one another. So you got to be careful there. So mass is density times volume. Well, we know the volume of this chunk of fluid. We can put it in terms of these deltas, right? So here we have it, delta x, delta y, delta z, and then times g as well. Okay, so what do we have it? So I can express this gravitational force in terms of the volume of this chunk of fluid, as well as some, constants that I could look up. I know what g is. I could look up what rho is for almost any fluid that's well characterized. And this gravitational force is acting in the minus z direction, so I can subtract it over here. All right. So bear with me. I know things are getting a little cumbersome, but simplicity is on its way. Get ready. Okay, so here we go. Let's now divide this entire equation by delta x, delta y, delta z. So let's divide by delta x, delta y, delta z, and do a little rearranging. So I'm going to flip-flop the order of these terms and divide by delta x, delta y, delta z. So what's that going to look like? I'm going to have 0 equals the delta x's and delta y's. If I divide everything by delta x, delta y, delta z, the delta x, delta y cancel out, so I'm left with just a delta z in the denominator here. And then dividing this by delta x, delta y, delta z, I get just minus rho g here. If I take the limit, you might be looking, hey, wait a second, this is looking awfully calculus-y, Professor Lannon. I would be like, yes, it is, indeed. So if we take limits, as delta z goes to 0, then we arrive at this expression here, which is 0 is equal to minus dp dz minus rho g. And this is basically true. This is something that's true for hydrostatics. Woohoo! Success, right? So what does that mean? We've gotten ourselves an equation. Ooh, it's a differential equation, but it's a differential equation that essentially, in some way, kind of implicitly in a buried way, can maybe relate a pressure gradient to some properties of the fluid and the system that it's in. Spoiler alert, this is kind of useful, but not the most useful result that we're going to get. So stay tuned for a more useful result in just a sec. So we have this result right here. Now, if pressure is a function of z only, which it should be in hydrostatics, right? We shouldn't have any pressures in x or y. So pressure should be a function of z only, and in hydrostatics, we can't have pressure be a function of time. So if pressure is a function of z only, strictly, these should be ordinary derivatives rather than partial derivatives. Again, we'll deal with these differences between ordinary and partial derivatives later on in the class. But there we have it. So if pressure is a function of z only, we can have it here. But again, you know, this differential equation is meh in terms of how useful it is. I think what most people want to know is, for example, if I had a swimming pool and I swam down to the very bottom of that swimming pool, you know, what would the pressure be? You know, if I had some swimming pool and I wanted to know, hey, how much is the pressure pushing on the walls of my swimming pool? You know, if I put a little plug in it, is the pressure going to be so much that it pushes the plug out? Something like that. This equation isn't really going to directly give us this answer, right? So differential equation, meh, in terms of usefulness. I would rather have some kind of expression that maybe can relate the pressure at some point up here and some point down here in the flow or in the fluid, right? So, you know, a differential equation doesn't really lead me to many insights, but something that relates a pressure at sort of two separate points in the fluid, that's going to be a lot more useful. So if we have this differential equation, we can manipulate it a little bit, we can integrate it, and that can give us a relationship between these 2 points, right? So how's that going to help us? Well, we can relate, so your differential equation, meh, but we can use this, we can integrate For example, we could use this to relate a point at the surface and the point at the bottom, the pressures and depth differences between those two points would we can get a relationship between these two. So if we have this differential equation, as far as differential equations go, this actually isn't too bad to solve. So we can try to separate variables and integrate. So integrate and separate variables. So I'm going to move dp dz over to the left-hand side of the equation, and then dz back over to the right-hand side. So I'll add dp dz to both sides, and then multiply both sides by dz. So I can get dp is equal to minus rho g dz right here. And then if I wanted to, I could integrate both sides to get to some final result. Now, we're moving towards a pretty useful result, but we haven't gotten all the way there. We can get all the way there if we make a couple interesting assumptions. So one assumption, which I think is a pretty good assumption, is that gravity is equal to a constant. So, if G is a constant, what can you do? Well, if G is a constant, so if we assume that G is a constant, then we can pull it out of this integral, right? And this is a pretty reasonable assumption, right? Unless you're dealing with, for example, like atmospheric physics, where like you're moving from like the surface of the Earth all the way out to deep space, where gravity varies appreciably over the whole distance that you're trying to analyze something. Unless you're dealing with something like that, then G it's pretty safe to assume that G is a constant. Another thing that we might want to be able to do, and often we can do, but not always, is if we assume that density is equal to a constant, then we can pull density out of the integral as well. And this one is a slightly more restrictive assumption. This basically means that we need to keep within one type of fluid. So for example, we can't pull density out of the integral if instead of being at the bottom of a swimming pool, I was at the bottom of a giant bottle of oil and vinegar, balsamic vinaigrette or something like that, right? So, we wouldn't be able to make this assumption, if I couldn't relate these 2 points quite so directly. If I, were in one type of fluid that had one density, and then I changed densities to a different type of fluid, right? In that case, density wouldn't be constant, so I couldn't pull it out of this integral because it would be changing with z, right? So, we got to keep within one type of fluid, and the fluid must be homogeneous fluid too. So, for example, I can't have, something like the atmosphere of the Earth, where close to sea level the atmosphere is pretty dense, but if you go up to 20,000 feet, the density of air is a lot thinner, something like that, right? But in many problems in fluid mechanics and in biofluids, you can at least make this assumption. And if you have the case where you have like oil and water, you can oftentimes break up your integral where you do just one part of it in the water, create some relationship at the interface, and then a separate integral for the oil. So a lot of times you're going to be able to pull density out of this integral right here. So let's do that. So now we have this integral dp is equal to minus rho g times the integral dz. All right, now we've made some progress. So if I do integrals, what can I do that? So how can I set this up? Well, let's sort of formulate these in terms of definite integrals. So let's say I have 0.2 and 0.1, and I'm not dealing with the case where it's oil and water. Let's just say the whole thing is water, or the whole thing is some homogeneous fluid, and I was able to safely assume that, right? So I could say, for 0.2 and 0.1, there's some pressure at 0.1, and there's some z height at 0.1, right? So maybe I have my z coordinate right here. I might say that there's some pressure at 0.1 and some z coordinate that corresponds to that point. And there's some pressure at 0.2 and some z coordinate at 0.2 as well. Well, if I integrate dp, then I get p, and if I evaluate that integral at p2 and p1, then I get p2 minus p1 on the left-hand side for doing this definite integral. If I integrate dz, then I get z, and if I evaluate that integral at z2 for my upper limit and z1 for my lower limit, and I keep this minus rho g out front, then what do I get? I get rho g times z2 minus z1. And now what is this? This is something where if I, let's say, like knew the depth of this, the depth of this point, I could relate the pressures at 0.1 and 0.2 as well. So, for example, if I knew 0.1 was atmospheric pressure, And let's say I just defined this point 2 to be z to be z equals 0, and I knew the depth of this pool was h, then for example I could say, hey, the pressure at point 2 would be equal to, and I could bring the p atmosphere to the other side. I could basically say it's atmospheric pressure minus rho g, and then z2 minus z1 would be 0 minus h, which then I could basically say, you know, P2 is equal to P atmospheric plus rho GH. Oops, sorry, I got cut off a little bit. Plus rho GH. That's an H over here. So what does this mean? The pressure at the bottom of my pool is higher than the pressure at the top of the pool by this rho GH quantity here. So anytime we get some result like this, it's useful to do a sanity check. So if I think about pressures, pressures ought to have units of newtons per meter squared, right? Pressures have got to have units of newtons per meter squared. And then if I think of, right, so pressure, and then if I think of rho g h, well, that better end up with units of newtons per meter squared too. Otherwise, you know who is going to be very, very upset. So rho g h, here we have it. Density is going to have units of what? Well, baby, before we get too far, pause and ponder. Do the units work out for these two quantities? So spoiler alert, they do. So density is going to have units of kilograms per meter cubed. G is going to have units of meters per second squared. H is going to have units of meters. And this Newton per meter squared is going to be kilogram meter per second squared per meter squared. And if you look at it all, we have kilograms. You know, we have kilograms on each side of the equation. We have seconds squared in the denominator on each side of the equation, and we have meters in the denominator over here because the meters cancel with one of the meters squared, and we have meters squared in the numerator with meters cubed in the denominator. So all of this and all of this are equivalent as well. So the units check out, and baby, you know who is very, very happy. So I wasn't being entirely cheeky at the beginning when I was talking about this blood pressure cuff right here. Hydrostatics is a very useful concept when talking about blood pressure. So for old school blood pressure devices, for old school blood pressure manometers, they had a tube that was full of mercury. And I'll just do mercury in yellow, even though we know it's a silvery liquid. And basically they had a little port at the bottom that you could attach to the bladder, the air bladder that wrapped around your arm. And then there was a pump, and the user would pump up the air pressure in the cuff, which basically restricts the blood flow in your arm, right? So I'm just gonna Right? So a person's arm is going through this blood pressure cuff, and they would pressurize this cuff with air, and basically the pressurized air would essentially force mercury up this tube right here. And a way that you could measure what the pressure was, what the air pressure was inside the bladder that's constricting the blood flow, is by essentially reporting it as a height of mercury, right? So the height of the mercury is proportional to the pressure in the cuff. And so, and in a sense, it's basically this rho GH like quantity here, where rho would be the density of mercury, g would be the gravitational acceleration, and because these two are pretty reliably constants, you can basically infer what the pressure was expressed as a height. So it turns out that, basically these mercury manometers were so common that everyone got used to interpreting pressures as millimeters of mercury, right? And if you want to go between millimeters of mercury and what an actual pressure is in terms of real units of pressure, i.e. pascals, you can convert between the two by this idea of rho GH, where h would be the height of the column of mercury in millimeters. You would convert that to meters, multiply it by density of mercury, which would be in kilograms per cubic meter, and multiply that by a g in meters per second squared, and that's going to give you the relationship between pascals and mmHg. Or you can just type it into the Google search bar, blah blah blah, millimeters of mercury in pascals, and Google will do the unit conversion for you. But we don't want to rely too much on Google. It's the physical intuitions of this pressure as millimeters of mercury comes from these fundamentals of hydrostatics. So, what have we done? We've done it. We've determined a relationship between pressure, depth, density, and gravity. So we would know, for example, if you went to the bottom of the pool, how much you would be under pressure. So there we have it. All right. So thank you very much. Hope you have learned a little bit about hydrostatics, pressure, and pressure gradient, and good luck with your fluid studies. Thanks.